So some chapter 2 in class examples. The first one is to find the number of protons in the nucleus of each of the following elements. So we'll work through the first one, which is sodium. So we'll go and look at a periodic table. If you don't have one handy, go ahead and pull one up on your phone, get a paper one, your textbook, whatever you have, but get one ready. And we're going to look for sodium, which is the symbol Na. And it is element number 11. It's on the left-hand side in the first column. And because sodium has an atomic number of 11, it means that sodium also has 11 protons. Now, in a neutral sodium, this would also mean that it has 11 electrons. But that's not what the question asks. But it is important to just remember that these two are equal to each other when we have a neutral element, and all of the elements on the periodic table are written in their neutral form. The second one says here it's to determine how many electrons are present in the atoms of each element. And in this case, we can go ahead and assume that these are neutral because it doesn't say that they're ions. So we can use the same strategy. Magnesium is element Mg. It's in the second column right next to sodium. It's element number 12, which means that magnesium is going to have 12 electrons as well as 12 protons when it's in its neutral form. The next question asks us to determine how many protons and neutrons are in each atom. The images did not show up correctly here, so I went ahead and wrote in the elements so that you would have them. So gold is this first one. Au is gold. It's element number 79, which means there are 79 protons, 79 electrons, because it's neutral, as written here. And now we need to determine how many neutrons. And what we need to remember is we're going to take the atomic mass, or the mass number, and subtract from that the atomic number. And those two numbers are written here. The 197 is the atomic mass. It's in the upper left corner of the gold symbol. And 79 is the number of protons. It's the atomic number, and it's written there on the bottom left-hand corner of the gold symbol. When I take the difference between these two numbers, I get 118, which tells me that I have 118 neutrons. And the 0 here with the line through it represents that there's no charge. The end represents neutrons. And so I use these little shorthands to save myself some time and not write out neutrons and protons each time. The next one says to write the electron configuration of a neutral chlorine atom. So if we remember, we have our periodic table. Here, and these are our S elements, our D elements, our P elements, and then down here in the bottom with the lanthanides and the actinides, these are going to be our F block elements. So chlorine is over here in the P block, but it wants us to write the electron configuration. Now chlorine has 17 electrons that we have to account for. It's element number 17. And so if you remember from the reading, we're going to work our way across the board. And we're always going to start here. It's kind of like playing a board game. And this is the first row. Then we have second, third, fourth, fifth, sixth, seventh. I ran out of space. And so we're always going to start in the 1s block. And we're going to represent this by saying 1s1, 1s2. There's no 1p first row. There's no elements up here. Remember, helium is on this side, but we're going to move helium over here next to hydrogen. So then I'm immediately going to move down to the next row, which is 2s1, 2s2. Then I'm going to skip over into the second row, and it's going to be 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. I still haven't gotten to chlorine yet, so now I'm down in the third row of the S block, and then finally I get over to the row and area where chlorine is, and chlorine is actually going to be right here. So in this case, I don't get to count all the way over to the 2p6 block. I'm going to stop in the 2p5, and then I'm going to write everything out. So I started off, I had 1s2, and then it was 2s2. Then we skipped over to 2p6, then down to 3s2, and over to 3p, and then stop at chlorine, which is element number 5 in that row. Now the neat thing is, if I add up all of these exponents, the 2, 2, 6, 2, 5, that equals 17 electrons. So that's a way to always identify or check your electron configurations. So there is the final answer. The next one says to use the variable n to represent the number of valence electron shells. Write the valence electron shell configuration for each group. The first one is the halogens, so these are group 7A. The second to last column on the right hand side, because the last column are our noble gases. Because they are in group 7A, that represents the number of valence electrons that they have. So it's very similar to chlorine, because chlorine is a halogen. And the valence shell is always going to be the highest number. And so in this case, for chlorine, its valence electrons is this, the 3s2, 3p5. So if I want to represent that with using the value n instead of a number, I can say it's 3p ns2 np6. That should be a 5 to represent the 7 valence electrons. So that's a generic form, because no matter what halogen I represent, whether it's in the second row, third row, fourth row, fifth row, sixth row, seventh row, they're always going to have S2 and P5. The one thing that's going to differ is the 2, 3, 4, and 5 that plugs into the N. So oxygen's another one. The column of elements headed by oxygen, so oxygen at the top of the group. These are they're called chalcogens. They're group 6A, so they're going to have 6 valence electrons. And no matter what, they're always going to have NS2, because they come after the NS group. And then NP4, because they're one group over, they have one less valence electron than the halogens, giving them NP4. So the next question is about periodic trends, which in this case it says, using the periodic table rather than figure 2.9, predict which atom is larger. And the trend that we have to remember is that as we go, and I'm just going to draw a square because it's close enough, as we go across, fluorine is going to be the smallest element. And as we go up, fluorine is going to be the smallest element. So over here, we're going to say that it decreases in size as we go left to right, and it's going to decrease in size as we go from bottom to top. The other way of thinking about it is that it's going to increase as we go away from fluorine towards cesium. So looking at this, we have lithium or fluorine. Well, I just said that fluorine is going to be the smallest. Lithium is over here on the left-hand side, so we know that it's going to be larger than fluorine. So in this case, lithium is larger than fluorine. The next one says sodium or potassium. So it would really help to have a periodic table here at this point because you would need to know where sodium and potassium are. So in this case, we see that sodium is going to be a higher up in the column than potassium, which means that as we go down the column of group 1A, that the atoms are going to get larger, which means that potassium is going to be larger than sodium.